Hello, everybody. It's a pleasure to meet you all. Before I get started on physical fundamentals, I just wanted, let me take this out. I just wanted to give a bit of background on why I wanted to give this talk. And why should you care about the physics of this? So the way that I view quantum computing, there are kind of two different approaches to it. There is the sort of software side approach, which is computing first, and then there's the hardware side approach of quantum first. And most of you are computer science people, and therefore I imagine most of you generally tend to approach quantum computing from the software side, which makes a lot of sense, because by black boxing all the physics, you get to have a sort of cleaner basis on which to build your quantum algorithms and so on and so forth. But when we're doing quantum hacking, it's quite nice to know what the actual physical system that we're working off of is, so that we can find maybe novel ways to exploit them. And also, by sort of having an idea of the physical perspective of things, we get an opportunity to demystify these sort of magical unitary operators and Hamiltonians that we're working with into something a lot more tangible. And so the goal of this talk is largely to make quantum mechanics not be sort of a magical equation gifted from God on high, and to give a sort of more physical understanding of why we're able to do the things that we're able to do with quantum computing. I have a slide thingy. Does it work? Yes. Okay. So, just a quick outline of what we'll be going through today. First, I'm going to start with some mathematical background. Many of you will know this stuff. Many of you won't. That's why I'm going through it. The goal here is to make this talk as accessible as possible. I'm going to assume no prior quantum knowledge, and I'm going to assume no prior quantum computing knowledge. Just some basic linear algebra is all you should need to follow this. Of course, I'm going to use a bunch of examples from more advanced quantum computing systems, but I want to start from the basics. So we'll go through a bit of mathematical background required to understand unitarity. And then using that, we're going to rederive Schrodinger's equation from just the ideas of conservation of probability and Born's rule. And so this makes Schrodinger's equation a much more natural thing to deal with, and sort of lets us understand why is this a particular equation that we're working with. And then we're going to go into the two different broad categories of quantum computers that are being developed right now. These being gate quantum computers and adiabatic quantum computers. These sections will be a bit disjoint because the gate and adiabatic computers are quite separate. But at the end, we're going to do a sort of broad question thing, because I have no idea how long it's going to take me to go through all of this, and so I might have a bunch of time at the end. Might not, I don't know. But if there are any sort of general questions, you can ask them at the end. But during the presentation, please do feel free to interrupt me. If you don't, I will not stop talking. So if I say something confusing, please, I don't know, raise a hand, shout out, something. It might be hard for me to hear you because I ruptured my eardrum last night, so hand would be nice, but whatever. And at the end of each of these 4 sections, I'm going to have a little questions area for that specific category. Also, there are going to be a number of derivations that I'm going to go through in this talk. The derivations aren't that important. If you don't get them, don't worry. They're there so that it's very clear what are the assumptions that I'm making and how those assumptions lead naturally to the conclusions that I'm drawing. If you don't understand the derivation, it's fine. The important results will be boxed, and I'll go through them, and all that really matters is that you get sort of what are the assumptions coming into this slide, and what are the results that we get coming out of it. Alrighty. I need to hold this. Okay, so to begin, we're going to see how, like I said, conservation of probability through Born's rule implies unitary time evolution. And also, what in the world is unitary time evolution? Before we do any physics, we need some notation. Again, many of you have seen this if you've done any sort of quantum computing. If you haven't, this is just a different way of writing vectors and covectors that quantum people love to use because it makes our expressions a lot neater. So this is called a ket, this is called a bra. A ket is a vector, a bra is a transposed vector. This is a dagger, means complex transpose. If you're unfamiliar with complex transposes, just think of it as the complex analog of a transpose. Really, it's a complex conjugation into transpose, plays much the same role as a transpose on real vectors. Together, these make bra and ket. This is bra-ket notation. Haha, the brackets. And with these bras and kets, we can write down many common expressions. Like, for example, an inner product. We write bra u, ket v. Now you'll notice how when we write a bra and then a ket, these like double center lines get merged. So yeah, that's just basically shorthand. But you know, following these definitions, this is a u complex transpose times v. That's how we do an inner product, right? So these are just alternate ways of writing the things that we know and love. As well as we can do magnitudes here. Bra v ket v is magnitude v squared. Any question on this so far? Okay. These expressions can get kind of ugly. And this is why we do bra-ket. Because using bra-ket notation makes it a lot clearer where the scalars in our expressions are. So here we see this is sort of an expression that would be quite ugly in our standard linear algebraic notation. But when we write it in bra-ket, it's very clear, like bra u, abc, ket v, that's a scalar. And scalars are nice because they compute with everything. So we can move that around and do some reordering operations and all that kind of stuff. So this is either the most important or least important part of the talk, depending on the view that you take on this stuff. I think it's quite important. We're going to go through the sort of three assumptions that we're going to be making. And there hopefully shouldn't be any other ones that we make throughout this talk. If you think I've made an assumption and I haven't stated it, please point it out. So we're going to make three hypotheses, assumptions, whatever you want to call them, that let us build up quantum mechanics. The first one is superposition. So this is if psi represents a state and phi represents a state, then phi plus c represents a state. Now, what in the world does that mean? Well, superposition is actually it's a classical concept. It's not a quantum concept. It comes out of waves, right? If I have, say, one electromagnetic wave, right, and I have another one, the sum of those two waves is yet another electromagnetic wave. What the superposition statement says is that the different parts of a state don't really interact. They kind of exist on their own, and this lets us make linear combinations of states as we desire. Because we can add states and scale them and so on, this means that we can represent states as a vector, ket, psi, we use kets, by writing them as linear combinations of the basis states. When I say the basis states, it's any sort of set of independent states that you can use to write down all of the states that we want to use. Now, some more things to say are, I've been saying represents a state. So we have states, which are a physical thing, right? There's an electron in an orbit, right? That exists. It's doing something. That's a state. We can represent these states with symbols. We can name the state, call it psi. And we can represent these states by state vectors. I might conflate the words state and state vector throughout this talk. I'll try not to. Because of this superposition principle, we can represent states as vectors whenever that's desired. So our second assumption will be that operators respect superposition. That just means that a of ket phi plus ket psi plus ket phi is a of ket phi. Yeah, a of ket psi plus a of ket phi. So all operators are linear. This is great because it means we can do linear algebra on them, right? Now that we've shown that states are vectors and operators are linear, now everything is like, oh yeah, we have all this machinery from linear algebra that we learned in whenever, and we can use that on quantum mechanics. Finally, there's Born's rule. Now this one's a bit ugly. Getting that feedback. So Born's rule is a bit ugly, and it's the only sort of ugly assumption that we have to make when we're going through all these derivations. And the reason for that is because Born's rule is what connects quantum mechanical states into physical things. This tells us how to do a measurement. Now, it says measuring state, psi, in state, phi. What does that mean, right? And so to sort of intuit this, we need to keep in mind that not all states are independent, right? So let's say that we can imagine an electron around an atom, right, from high school chemistry. We have an electron going around an atom. It's in the second orbital or whatever, right? And it's kind of just buzzing around, and that's fine. Now I'm going. Let's call that state psi, right? Now I'm going to define this state phi to be the electron is on the northern half of the atom, right? Just it's on the northern half. That's fine, right? And the probability that we measure state psi in state phi corresponds to in this idea. What is the probability that the electron is in the northern half of the atom? And the expression written here is this, which is a bunch of inner products between our states, vectors, and this denominator, which is a normalization factor. You might think of, if you've seen like the angle between two vectors, as this like inner product divided by a bunch of norms. Remember, these are the norms squared of our state vectors. And we'll see in a bit how we can clean this up just a smidge. Any questions so far? Okay. I'm going to, oh yeah.
Can you come up here to do questions, please?
I can just repeat the question, it's fine.
That's fine if you can.
Yeah. So the question was, what does a state physically represent? So a state is just what is happening, right? Like what is the, if I flip a coin, right? The state can be heads or tails once it's flipped, right? There are two states that it can be in. In quantum mechanics, we have some electron, right? Or going around an atom, right? The state could be it's in the 1s orbital, or it's in the 2p orbital, or it's in a superposition of the 1s and 2p orbitals, or it's in some hybridized fancy chemical stuff. I don't know, I'm not a chemist, right? But we can represent what is actually going on with this electron. That's a state. Does that make sense? Okay. There was another question, I think? Yeah? The question was the denominator in the measures is 100% probabilities. I'm not sure I understand I'm not sure I understand what that question is. Yeah, this is the probability of measuring psi and phi. Yes. Right. Okay, so the question, which was more just a true statement, is that so this denominator is the maximum value that this numerator can take, just by the laws of linear algebra. And so that means that the probability is maximized when this numerator equals the denominator, and that equals 1. And that's what we're going to see on the next slide. Yeah? Can I move the mic stand to the right? Yes. Okay. So let's tackle using Born's rule a little bit. I keep putting this in my pocket backwards. Okay. So let's look at a state phi, which we're going to define to be alpha times psi for some alpha that's non-zero in the complex numbers. The probability of measuring our state psi to be in the state phi is given by Born's rule, and we can just expand that out to get 1. That means that psi and alpha psi represent the same physical state. So this complex factor in front, which it changes the phase, and it like the global phase across all of the components of the vector, and it changes the magnitude, doesn't actually matter. Ooh. And so to make these things a little bit more convenient, we're going to call a state psi normalized if the norm of psi is 1. That means that this denominator disappears, right? And now Born's rule just says that the probability of measuring a normalized state psi and a normalized state phi is this numerator, which is a lot nicer. And we can make it even nicer. So Now the thingy isn't working. Oh, there it is. Okay. So let's inspect this object. This is called a dyad. Dyad is just a ket and then a bra instead of a bra and then a ket. And this is not a scalar, right? Remember, bra is ket. That's an inner product. That's a scalar. This is an outer product if you're familiar with those. But if not, just think of it as a vector, column vector times a row vector. We get this matrix coming out of it. And this dyad is quite nice because if you square it, you get back the original because that's going to be. Oh, I have this laser. I keep forgetting. So that's going to be ket psi, bra psi, ket psi, bra psi, and this middle term would disappear because the norm is 1. So that means that this dyad is a projection operator. It projects down onto the component of the wave function that corresponds to phi, not phi. And so we can write down sandwiching this dyad between our bra psi and our ket psi. We get back this Born's rule expression. This was the numerator from the last page, which is equal to the magnitude squared of the phi component of psi. This might be what you've usually heard of Born's rule as, that the probability equals the magnitude squared of the wave function. But in this formulation, we get this out of this idea of defining what even is a measurement. Actually, before I move on, any questions on that? Okay. So now we're going to look a bit at transformations. And we're going to show that the conservation of probability, we want probability to always sum to 1, is going to give us unitarity, which I'll explain what that means in a bit. So we're going to consider a transformation U that takes psi to U psi, that takes states to states. So this is an important bit. We're talking about something that takes states, and I'm going to say normalized state vectors to normalized state vectors. So some examples of that might be translate space over, right? You have your electron over here on this atom, move it over there. That's a new state, right? It's not a very nice state. The electron doesn't want to be over there, but it is over there now, okay? That's a state. Or we can rotate the whole universe, or we can, translate time forward, right? Like any sort of operation like this, make a reflection. These take states to states. And we want to see the properties of these operations. So first off, we said it takes normalized states to normalized states. So this means that we need this normalized inner product to be 1, which means the determinant of U dagger U is 1, which means that the determinant of U is 1. And then now we can tackle conservation of probability. So that means that, so if I have two states, right, like my 2s orbital from before and my northern side of the atom from before, right, and I move it over there, right, I move both both psi and phi over there, right, the probability of that new psi being in the new phi state should stay the same as it was before, because we just moved the whole universe, right? And so for that to be the case, we need this to stay the same once we apply our U. And I'm not going to go through the derivation for this, but this means that U dagger U equals the identity. This is a very nice property. This is called unitarity. And it's going to be critical for pretty much everything that we do going forward. And we will revisit this in a bit and see how this is useful. Also, I'm probably going to stop asking, do you have any questions? So just interrupt me. Ooh, jeez. Oh, it's the next one. Okay. I'm safe. Okay, I guess I'm doing this example before the other thing. Fine. So, now we're going to talk a bit about measurement. So, we can implement arbitrary physical measurements as a linear combination of state measurements. And we can do this by sort of decomposing, like, if we have various states that we know the measurement in, and these states form a basis, then we can form a linear combination of those with respect to the measurement quantity that we want and get out a result. So I'm going to demonstrate that here. So let's say that we have a very simple system. It has two possible locations for a particle, x1 and x2. They're -4 millimeters and 12 millimeters respectively, right? We can define this operator capital X to be minus 4 millimeters times this x1 dyad, which remember is a projection onto x1, plus 12 millimeters times this x2 dyad. So the expectation value of x under a state, which this is the probabilistic definition of expectation value, right? Which is it's the thing that we're measuring times the probability of measuring it summed over all the possible measurements, right? We can calculate this by sandwiching capital X in this psi expectation value. So we get minus 4 millimeters times the probability of psi being in x1 plus 12 millimeters times the probability of psi being in x2. This is kind of a bit of a backwards derivation. I gave you an example and showed how it satisfies the properties that we want. This sort of gives a intuition for how we might construct these measurements. And so we can do an actual example. Let's define this state psi. So it has a 1/4 probability of being in x1 and 3/4 of being in x2, which we see because, remember, we have to square those coefficients to get the probability from Born's rule. And we assume that x1 and x2 are mutually independent, right? If you measure something in x1, it's never going to be in x2, right? That's what this is saying. Then we can get that expectation value of x by just writing out this, doing that inner product, and we get 8 millimeters, which is reasonable, right? If you have a 75% chance of being in x2, the 12 millimeters, the math works out, assuming I didn't mess it up. And we can take this a bit further. I'm not going to go super into this, but what's nice about this way of constructing measurements is that we can compose measurements to make new ones. So, if we want to get the expectation value of x squared, we could do it by taking the expectation value of this operator x squared. Now that might seem a bit, wait a minute, why can we do that? But we should just actually take a look at x and imagine squaring it, right? So you're going to get these, it's like a squared plus ab plus ba plus b squared, right? And that first term is going to be minus 4 millimeters with this dyad times minus 4 millimeters with this dyad. And those two dyads, it's a projection, so they'll combine back into one dyad. The cross terms are going to cancel because x1, x2 is 0. And the last term is going to be 12 millimeters squared times, again, this projection squared, which is equal to itself. And so this sort of lets us construct these composite operators and build up any sort of measurement off of just a basic set of measurements. Any questions on this example? I guess I lied about saying I wouldn't ask. Okay. So, now we can generalize this. In general, for any measurement of a real quantity, and by here I say real as in like in real life, but also real as in real valued, right? Because you're never going to measure the position of a particle and have it be, yes, this particle is at 1 plus 3i millimeters, right? You're always going to have real valued quantities. And so what that means is that the expectation value of A should always be real. This means we can take the complex transpose, because this is a scalar, right? So the transpose is the same thing. And the complex conjugate of a real value is itself. And distributing out that conjugation, remember the conjugation turns a bra into a ket and vice versa. And we have to change the order of things. That's just a linear algebra rule. We get that we can conjugate transpose A. We can also take the average of those. And what this shows is that we can represent any measurement by an operator that satisfies A equals A dagger. By sort of, if we have a measurement that isn't like that, we can just take the average of it with its transpose to get one. This property is called a hermiticity. It's Hermitian. And so, combining sort of the things from before, we have that all transformations are unitary, satisfying this, and all measurements are Hermitian, satisfying this. Any questions on that? I think the next thing is going to be a bunch of examples. No, it's literally just a slide that says questions. Questions. This is all we're doing on math background. So if you have any questions on anything that's come so far, now's the time. 3, 2, 1. Okay. Go on. Oh, yeah. Sorry, I can't hear you. Can you go over to the mic?
Hello? Yeah, okay.
Hello.
Yes, right now, yes, okay. So this question might not make sense. I'm not that deep into the math. Okay, yeah. So, in real life you can, as you said, get the right position. Would you just choose an arbitrary state and just compare to that to get like a relative position, you know what I mean?
I'm not sure I understand the question.
So, you said... Oh, wait a second.
Do you want me to go back to the position slide?
Yeah, exactly.
Yeah, yeah. So here?
Yeah, right. So in real life, when you don't have the position, you can't like determine them. But can you compare them? Like if you choose an arbitrary state, let's say this is just like this state, can you compare another quantum to this state to get like a relative position?
Oh, to do relative positioning. Probably. I mean, like, you can just define your measurement, right? Like, define this x to be relative to one of these, right? Like, have this be 0 and this be 16, for example.
Yeah.
Right? And that's fine, too.
Okay, so this is possible. Okay.
Yeah.
Oh, thank you.
Of course. Any other questions? Okay. Alrighty. Now we start getting into some actual math. This is physics. Some actual physics. So, goal of this section is to rederive Schrodinger's equation. We're going to get it straight out of the stuff that we've done so far. No other assumptions, hopefully. Okay? So, first off, let's say that we have an operator, right? A linear operator called u. Okay? And u is a time translation. Okay? It takes us translate from time t0 to time t. This, as we saw before, transformations are unitary operators. And we can see that by doing this derivation. This just rederives that any time translation will be unitary. But we get these various relations that should be relatively intuitive off of the idea of just having a time translation. I have a laser. Why am I using my finger? Laser. Okay. Oh, damn it. I right-clicked. Okay. First off, for all t, u of tt equals 1, this should not be surprising. If we don't translate time, or if we translate time from the time to the same time, it shouldn't do anything, right? So this is a nice result, a good sanity check. This one's a bit more interesting. It says if we translate from time 0 to time 1, then from time 1 to time 2, it's the same as translating from time 0 to time 2. Again, this is physically reasonable, but it's nice to see it in the math. And here you should note that we see these operators apply from right to left because the state vector is always going to be on the very right. So that's sort of the order in which you should view these things as being applied. Finally, we can make some substitutions to rederive unitarity, but we've already seen that, so we'll move on. Now, let's rederive Schrodinger. We're going to take a time derivative of our state psi at time t. Oh, I should explain this notation, sorry. So this is the state psi at time t. This is the state psi at time 0, right? The idea being that our state might evolve with time, right? That seems reasonable. If I have a ball that's over here and I drop it, later it'll be down there, right? And so this u sort of tells us it goes down. And so now we want to take a derivative of this definition. So we do that. We take a derivative on the left, take a derivative on the right. Note this bit is time independent. There's no t dependence here, so that's a constant. Now we can go back to t land by doing the reverse time translation. And then we can take the transpose I forgot to mention before. So the conjugate transpose or the inverse is the same as just flipping the indices, right? Because if you translate forward in time, then translate backward in time, we expect nothing to happen. So yeah, we flip that, and we define this expression to be this lambda of t0. And so we have this sort of proto-Schrodinger equation that appears as a time derivative. How do we define the time evolution of the state with this proto-Schrodinger equation? But it's a bit gross because it has this t0, and that's kind of lame, right? But this lambda that we've defined has two important properties. It's anti-Hermitian, and it's independent of t0. We're going to show those now. So again, these derivations don't really matter very much, but this is just that last line from before defining lambda. We do some math, and then we see, yes, look at it. It's anti-Hermitian. The sum of the lambda and lambda dagger is 0. Wonderful. And it's also independent of T0. We do that by showing that lambda of T0 is lambda of T1. Since we have these two properties, we can make some substitutions. First, take lambda of T0, or we're going to just replace that with lambda of T, because it's independent of T0. We don't need that variable, right? Second thing is lambda is anti-Hermitian. That's gross. We like Hermitian, so we're going to multiply it by I, right? Because when we multiply by I, taking the conjugate transpose, we have a negative from the anti-Hermiticity and a negative from the I conjugate, because minus the icon. Second of all, lambda has units of inverse time, because we derived it by taking a time derivative of a unitless quantity, right? That was over here, I believe. Yeah, so we took a time derivative of this u, and this u has no units, right? And so inverse time is kind of, it's an okay unit, but by convention, we multiply that by this h bar, which has units of energy times time, so that we get a operator that is Hermitian that has units of energy. Now, remember what we said before about our measurements being Hermitian operators. Hermitian operator with units of energy. It'd be nice if it measured the energy of our system. Maybe. We'll see. But, yeah, off of this substitution, we immediately get the time-dependent Schrodinger equation. Now, yeah, that's Schrodinger. You may have seen it a little bit differently. You may have seen it as h psi equals e psi. If you've seen it as that, that's what's called the time-independent Schrodinger equation. And that only applies when h is not dependent on time. And we could rederive it. I don't know. I don't remember if we do it later in the presentation. I made this last night. Yeah. So that equation works wonderfully if your Hamiltonian is time-independent. But we're going to be doing very general stuff here. When we're doing quantum computing, our Hamiltonians are pretty much always time-dependent. So this is the equation that we'll be using. Before I get on to the example, any questions so far? Okay. So here's an example. Electron orbits. These don't look like orbits. Yeah, they don't look like orbits to me either. But what we have is sort of an approximation, a low-dimensional approximation of what an electron's orbits might be. So this is, I believe, a CO2 molecule. This is the electron orbits of a CO2 molecule, just the first 3 energy levels. Now, you might notice that the first energy level is defined to be 0. This is because, for complicated reasons that I'm not going to go into, we can add any multiple of the identity to h0, and it just changes phases, which don't actually matter. And so this is our h0. We see that the second energy level is 0.0082 whatever the fuck unit more than the lowest energy level, and same goes for that second, is 0.016. I believe these are atomic units, which are like, you set like Bohr's radius equal to 1, some, h bar equals 1, shit like this, right? But just, this has units of energy. And so we also have this dipole term. And this reflects how our system responds under an external electric field, right? Or is it a magnetic field? I don't remember. But we write the total Hamiltonian as this h0, called this field-free Hamiltonian, or the time-independent Hamiltonian. And then this mu is this dipole times this scalar epsilon of t term. This is a field that we can make stronger or weaker. This is, you can just imagine we have a lever that can increase the amount of mu that we shove into our system. And what this does is this effectively pumps energy into some of these states, right? It might raise or lower the energy of various states that we had to start with, and it also creates some interactions between them. That's what these terms on the off-diagonal are. Now, another thing you might notice, this is a diagonal matrix. That's quite convenient. And it's that way by design. What we do, generally, is we write our states in the basis defined by the eigenbasis of the Hamiltonian. Now, what's the eigenbasis of the Hamiltonian? If you have done eigenvectors of matrices, then you might have a hint of what this is. But the eigenstates, or eigenvectors of the Hamiltonian, are the states that have a definite energy value. You might remember way earlier, we wrote our measurements as these linear combinations of these dyads, right? Now this x is diagonal, right? We could have had a like x2, x1 term. Then it wouldn't be measuring position, it might even be measuring something else. But we could have had an x2, x1 term. We're writing this in this basis, in this x1, x2 basis that represents the positions that we're working in. And so in the same way, we can write our Hamiltonians in an energy eigenbasis. That's just saying the states of definite energy, the states where when you multiply when you multiply h naught into your state, you get just that state times a scalar out of it, and that scalar being the energy of the state. And so this is really nice, because this means that if we didn't have this mu term, this equation just becomes a bunch of independent equations, right? Because there's this h of t isn't coupling anything. They're not going to be state 1 interfering with state 2 and so on. So you get these, very nice, like single variable exponential equations. We know how to solve those, right? But once we introduce this mu term, we start adding interactions between those states. And then what happens is that the time evolution operator that we construct is going to end up having something that maybe like the ground state will move up to this first state because, remember, we've pumped in energy with this electric field. Any questions on that? Okay. So, another example. And this is an important example that we're going to come back to a lot later. This is a nuclear spin in a magnetic field with a control field. Worth noting, a lot of the examples that I'm going to be using in this talk are relatively simplified, and they also might have sign errors or factors of 2. So if you're looking at this and you're like, oh, I thought it was the minus sigma y, maybe it is. I don't know. But this is enough to give you an idea of what's going on here, right? So we'll look at our field-free Hamiltonian first. Okay, field-free is a bit of a misnomer here. Let me talk about the actual physical system, okay? I want you to imagine you have a atom, okay? You have this nuclear spin in, I don't know, maybe in some molecule, maybe not, I don't care, right? It's this nucleus, right? Doesn't really interact with anything besides the nucleus, except for an external magnetic field that we can apply, right? Like we can put an electromagnet around our nuclear spin and call it to do shit. And so what we're going to do is we're going to apply a strong field, B naught, in the z direction. Why the z direction? Because I defined the z direction to be the direction in which we put this field, right? The coordinate system doesn't matter. So we're going to apply this constant field, B naught, in the z direction. So the Hamiltonian will pick up this term. So there are 2 states, right? As you can see by it being a 2-dimensional Hamiltonian, there are 2 independent states. One of them is the state that is aligned with the magnetic field of the environment that we've applied. This is a very low energy state, right? Because it's a very comfortable place to be, right? You have this nuclear spin acts like a tiny bar magnet, and we have it in this big magnetic field, so it wants to align with that magnetic field. That's this low energy state. Alternatively, it could be unaligned. That sucks. Higher energy, right? So that's our field-free Hamiltonian. It's just it doesn't have a time-dependent component. And so we sort of start with this system, and then we're going to apply another magnetic field to it. This time, one that we can control, right? So imagine, this is just a big, constant current electromagnet that's running all the time. Whereas this external magnetic field Maybe it's like a bunch of electromagnets that we're turning on and off to make a specific configuration, or maybe it's a radio wave, right? Something, right? That's changing with time. And so we get this external Hamiltonian that, again, adds some interaction between these, like, up state and down state, or whatever you want to call it, right? And I hope I have more on this slide. I don't. Okay, wonderful. This is pretty interesting because this control field, and no, this is two separate control fields, like we have two variables that we can fuck with. This gives us control over our quantum system. We can make it do stuff, right? Because if we just had this H naught, this would be a very boring system, right? It would either be aligned or unaligned, and it would just sit there. That's not exciting, right? But now we have this external field that we can control. We can make that qubit do stuff. Oh, I said the word qubit. Look at that. This is a qubit. What is a qubit? It's a system with two states that you can control. That's all a qubit is, right? So yeah, now it's a qubit. Now that we've added this stuff, now we can control this system and make it do stuff. We can make it do maybe computation later down the line.
Louder.
Yeah, can you say that louder? Yeah, okay. So two independent basis states, right? So we have this two-dimensional space, right, of states. So we might have, oh, I guess I can use my iPad now. Okay. Three-finger swipe, maybe, perhaps. Three-finger swipe. Three-finger swipe. Ah ha ha! Cable, oh yeah. Anyway, wonders of modern technology, I can draw stuff for you. So we have these two basis states, right? We have this, oh, hello, why is it being stupid? Anthony, I don't know how to use an iPad, help me. Scroll down? Okay. Tap the button? Okay. Okay, got it. This is not my device. So, we have our two basis states. We're going to call them up. Up is going to be the aligned one, right? So this will be the state 1, 0. And we have our state down. This will be the state 0, 1. These are the two independent states. Right now, we could have chosen a different basis, right? Yeah, it's sounding very binary, right? But remember our principle of superposition. We can add or subtract or multiply our states together to get new, sorry, not multiply states together, but we can add and subtract our states to get new states. So, for example, let's look at up plus down. This is the state 1, 1. Okay, that's not normalized. Gross. We're going to divide it by root 2 to make it normalized. Okay? That does nothing, right? It's still the same state because of what we saw before about alpha, phi, and phi being the same state. So now we have this state up plus down. This is, like you said, it's analog. It's in between up and down. It's a linear combination of up and down. But there's also not just one way that we can do that. For example, I could do up minus down times 1 over root 2. This is going to equal 1 minus 1 times 1 over root 2. These two states are different. They have the same probabilities of being measured in the up or the down state, right? It's equal probabilities. It's 1/2 probability of being in up, 1/2 probability of being in down in both of them. But the states might have different results for other measurements. For example, one of these might be pointing in the plus x direction, and one of them might be pointing in the minus x direction. And so that's sort of where the nice superposition properties come in, is we can take these states and we can combine them, but also not just in one way, right? Let's add another one. Let's do 1 over root 2. Error correction more comes in when you have some uncertainties and decoherence that happens. So like when your gates are imperfect, which we'll get to later, right? But when your sort of measurements are imperfect and your unitary transformations are imperfect and your Hamiltonians are imperfect, you start accumulating these various errors, and this might help with that. But the thing that I want to write here is this. So this is 1 and I, right? Because these are complex vectors. We can combine them in kind of any of these interesting, fancy ways. Yeah, that's the combination stuff. Does that answer your question? Okay. We'll get more into doing superpositions later once we get into gates, and that'll hopefully make it a little bit more clear. Any other questions on this? Okay. It worked. Okay. Here we are. We have another example. This is the last one for this section. So, the goal of this example is to show that we can have really abstract systems. We can kind of define our Hamiltonian, right, in theory, to be whatever we want. Really, whatever. As long as it's Hermitian, it's fine. This is missing an energy factor, but whatever. The issue comes in, okay, well, I've written down this Hamiltonian on paper. How do I make that happen in real life, right? That's a lot more difficult. That's kind of what all the engineering around quantum computers has been about. Or maybe not all, I shouldn't say all. A lot of the engineering has been about. This is an example taken from a talk from last Quantum Village. And this was a talk about using quantum computing to break lattice cryptography. It was a very cool talk. And I'm just stealing their Hamiltonian because I can. First, I know that there's like an E0 here because I forgot it. But for those who are unfamiliar with lattice cryptography, this is going to be very confusing. It's fine because we're going to move on after it. For those who are familiar, it's going to be very interesting. We have some basis for a lattice. This is just a basis that we can make integer linear combinations of. Any integer linear combination is going to be a lattice point. And the goal of breaking lattice cryptography is to find the smallest vector in that lattice. So like the linear combination of these basis vectors that has the smallest magnitude. And so we can define this Hamiltonian by defining these number operators. Let's say ni on C will give you n lowercase ni on psi, where lowercase ni is the number of times that this state represents. That this state. Oh, this says C instead of psi. Fine. Basically, our states here are going to be linear combinations of these lattice vectors, right? But they're going to be integer linear combinations. And there's a way to make that work. What becomes nice is we can write down this Hamiltonian for the lattice that is just this sum of these number operators. And so, this is like the number of, if you have a state here, this will give you the number of times that that bj appears times the number of times that ni appears times this inner product. What this lets happen is the ground state is 0, 0, 0, 0, 0, okay? The second lowest energy state is going to be the smallest vector in the lattice, smallest non-zero vector in the lattice, because we've just defined this Hamiltonian to build out that inner product. Again, it's very unclear how this would be realized physically, but it's a Hamiltonian that I can write down. I can write down whatever Hamiltonian I want. Does that make sense? Okay. Clicky, clicky. Okay, any questions on that past section? Yeah. So the question was, why are shortest vector problems and... used in post-quantum computing? They're not, because we can solve them with adiabatic quantum computing. I mean, yeah, we use different problems, like lattice problems with errors.
You'll find out in the next talk.
Yeah, cool. But yes, we don't do that kind of lattice problem because, as you just saw. Well, I mean, we'll see later. We're going to come back to that system later, just like we're going to come back to the nuclear system. Any other questions? Okay. Bing. So, fancy slide. So, we've finished our physical background. We've derived Schrödinger's equation. It's great. Now we get to do actual computation. So let's start with gates. Okay. To do gates, we have to talk about piecewise constant Hamiltonians, right? So, if our Hamiltonian is time independent, we can solve Schrödinger's equation for this time evolution operator by just taking what's called a matrix exponential with this time difference. This is just differential equations with matrices. If you've seen it, it's familiar. If you haven't, it's not. Just trust me. This solves the equation, right? You might imagine taking a derivative of this equation with respect to t1. You see, we get this minus I over h bar h naught. Multiply that by I h bar, and you get h naught times u of t1 to 0. Great. Solve the equation. And this is great and all, but constant Hamiltonians are boring. Let's add some dynamicism. I'm going to say before this splitting time, Ts, our Hamiltonian will be h1, which is a constant. After, it'll be h2. How do we solve this? Well, we can do the same sort of thing, and I'm not going to go into the proof that this actually works, but it might seem reasonable physically that we have this. First, we do this time evolution from the first Hamiltonian up to the splitting point, and then we do the time evolution from the second Hamiltonian after the splitting point. This is, of course, assuming that the splitting point is between our start and end time. And so we can construct like arbitrary approximations to any sort of continuously varying Hamiltonian with these piecewise constant pieces. This is generally how computationally you construct these gates and simulate these gates, is with these piecewise constant systems. Not always, but generally. And so we can see how this gets applied for a 1-qubit gate. What is a gate? A gate is a unitary operator that you construct. That's all it is. A gate is just, I want this thing to happen. This unitary operator, I want it to transform my quantum system in some way. That's a gate. It's called, this one's the X gate, I think. Please correct me if I'm wrong, but that's the unitary operator that we want to construct. This is the representation on the block sphere, if you're familiar with the block sphere. If not, don't worry about it. And here is the actual the actual like magnetic fields that are being applied to our nuclear system, right? Like this is we're on this. We're back at that example with that single qubit in a nucleus, and we had that X magnetic field and that Y magnetic field that we can control. This is that. This is those fields, and you see they're piecewise constant because we like that. It's nice and easy to calculate this kind of stuff, and yeah, it causes, if you apply this field and you look at the resulting unitary, you get an X gate, right? And this is generally the point at which that black boxing happens. So usually as a quantum computing person, you're like, okay, I'm going to apply an X gate. And some engineer somewhere has to figure out the actual field to do it. But we're running out of time, so I'm going to speed now. Let's talk a bit about coupling qubits. We've talked about 1 qubit. What if I have 2? Well, those two qubits are going to interact with each other, right? Because they have their own, they're tiny bar magnets, right? They have their own magnetic fields. They're going to have an extra energy term for the alignment of those two magnetic fields. And so that means that when we actually do, when we want like an X gate, it's going to be a lot uglier, right? This is an X gate on 3 qubits. It's on just one of them, right? This is X gate on the, I don't know, first, third, whatever you want to call it, qubit of this system. And what you're seeing is the probability amplitudes in the state over time, over the duration of the gate. So at the start, it's in this 0, 0, 0 state. Then it has a bunch of complicated superposition bullshit in the middle, right? Just trying to do magic to get over here in this 0, 0, 1 state, right? This is an X gate. Someone sat down and designed this gate, right, with a computer, right? But whenever, in your like KISS kit, you do like .x or whatever, this is what happens, right? So the hardware exists, and it has to actually make the gates. Now we'll talk a bit about gate universality. First off, can we do all classical computations on a quantum computer? Yes, I think. Please, but yes. So this is basically a NAND gate. It's called the Toffoli gate. Did I? Yeah, I did. So we have these inputs. It takes in 3 qubits. You have these inputs, these outputs. We see it flips the last qubit if and only if the first 2 qubits are on, right? This is a NAND gate. If we can make a NAND gate, we can do any computation, right? That's a universal gate, classically. But how do we make this gate? Well, turns out we can construct arbitrary unitary operators out of just a few gates. This is what makes gate quantum computing so powerful. Because it's like building computers, right? Like you have your silicon, you can do a few things with it, right? But you combine that stuff together into this big powerful processor. And so we can construct any unitary transformation by just applying these 3 gates in fancy orders on our system. And of course, you'll apply it on different qubits, but yeah, universal set of gates. This means that we could, for example, construct that Toffoli gate from before off of these 3. Any questions on that? Okay. So I have 2 minutes.
You have very hard 2 minutes.
Okay. Speedy. Instantaneous eigenstates. At a given time, right? Our Hamiltonian is in some form. There is an eigenstate at that moment, right? These are in general, the eigenstates will time evolve, but in a moment, there's an eigenstate, right? Now let's imagine our nuclear spin example from before. If we have a nuclear spin in a strong magnetic field, right? And we start weakening that field, that up state will stay up, right? Eventually the field will flip, but the up state will stay up. That means that it changed from being the 1 state to the 0 state, or whichever, right? That's gross. But it turns out that doesn't actually happen in real life because of this nice thing called degeneracy braking. So if we have a very weak transverse field, instead of the field going to 0 and then going down, the field actually goes near 0 and then flips around. And if we do that slowly enough, then our qubit will actually follow that field and go from up to down. This is called adiabatic quantum computing. The slowly enough is defined by the gap between those energies at the closest point. So divided by h bar or whatever, you get a gap. Just stop me whenever it's time. So this general idea can be generalized to the quantum adiabatic theorem, which says that under a slowly changing Hamiltonian, which again, defined by these energy gaps, the instantaneous eigenstates stay in the same ratios when we evolve with time, right? Like that lowest energy, if it's 50% chance in the lowest energy, it will stay 50% chance in the lowest energy, which lets us do computation. Let's say that I want to minimize this function, right? I can start with this Hamiltonian, right? Where my lowest energy state, my system is in the known lowest energy state, and then very slowly, right, change it to this Hamiltonian, right? And the system will end up in the lowest energy state, which will be well localized in that minimum of the Hamiltonian. We can use that on our lattice thing from before, and apply this concept. We can say that at time negative infinity, our system will be in H naught. That's some known Hamiltonian where we can prepare the particle in the lowest energy state. And then we can very slowly vary it to that lattice Hamiltonian. Then our particle will end up in the lowest energy state of the lattice Hamiltonian, which is the solution to the lattice problem.
And I think that is the moment to finish on. Thank you very much.